In a previous video, we talked about the relationship between the lengths of the sides in a 45, 45, 90 triangle. And in that video, we discussed where this relationship that's shown in this diagram, or this equation, where that comes from. Today, what we're going to be looking at is what the types of problems are that you will see using 45, 45, 90 triangles. Typically, in problems of this type, you're going to be given the length of either one leg or the length of the hypotenuse, and you'll be asked to determine the lengths of the other two that aren't given. So we're going to look at examples in this video of each of those possibilities, given the length of a leg or given the length of the hypotenuse. So let's start with this first one. Now, in this first one, we're given a 45, 45, 90 triangle whose leg has a length of 9. We know that because the triangle has two 45-degree angles in it, two acute angles with the same measure, that means we have two legs that are congruent. So in this case, since the legs have to be congruent, that tells us the other leg has to have a length of 9 as well. Now, we also know from this equation and this relationship that we see in the triangle that if we multiply the length of the leg times the square root of 2, that'll give us the length of the hypotenuse. So in this case, if we take 9 and multiply it by the square root of 2, we can't simplify that at all. There isn't any other radical that the square root of 2 is going to combine with. In this case, that multiplication is already simplified, so the length of the hypotenuse would be 9 square root 2. And that's what happens when you're given a leg length that's a whole number. In this next example, we want to look at an example of a leg length that's not a whole number. And in this case, our leg length is 5 times the square root of 3. Okay, so the same process applies. We know that the legs have to be congruent, which means the other leg will also be 5 times the square root of 3, and that the length of the hypotenuse has to be the leg times the square root of 2. So in this case, we're going to take that 5 root 3 and multiply it by the square root of 2, and that's going to give us the length of the hypotenuse. Now, in the case where you have two radicals being multiplied together, you simply multiply the numbers inside the radicals, which are called radicands. This whole number 5 is only going to be changed by other whole numbers. So in this case, this 5 remains unchanged. The root 2 and the root 3 are going to multiply together to give us the square root of 6. Now, the one thing you'll need to do with any of these that involve a square root is double check and make sure that your radical is simplified. Here, the square root of 6 doesn't simplify any further. So 5 square root 6 represents the length of the hypotenuse. Okay, so that's the two possibilities that you'll have given the length of a leg. Either a leg that's a whole number or a leg that's not a whole number. Now let's look at some examples where you're given the length of the hypotenuse. In this first example, we see a hypotenuse that has a radical contained in it. 8 times the square root of 2. We know that the legs have to be congruent, and that if we multiply the length of the leg times the square root of 2, it has to equal 8 square root 2. Now, if we go back to what we know about equation solving, if you were to have a variable here, let's say we were to call that x. To get x by itself would mean we would need to divide both sides by this square root of 2. So in this case, x represents the length of either leg. So if I divide both sides of this equation by the square root of 2, undoing that multiplication by the square root of 2, this is going to cancel on that side, leaving x, but we'll notice that on the right side, these square root of 2's also cancel, leaving 8. So the length of the leg in this case would be 8. And since the legs have to be congruent, they would both have a value of 8. Now, that particular one is fairly simple to take care of because of the fact that the hypotenuse had a radical 2 already contained in it. But the question naturally becomes, what if this radical on the hypotenuse isn't a square root of 2? Or what if the length of the hypotenuse doesn't even have a square root in it? Then what do? Well, it still goes back to this division, but your division changes slightly. All right, so let's look at this next one. In this next one, we've got a hypotenuse whose length is 2 square root of 3. So I want to take the same approach that I did before. And here we're going to refer to our legs as x. So the length of the leg, x, times the square root of 2 has to equal, in this case, 2 square root 3. And there again, to get rid of that multiplication by the square root of 2, we're going to divide both sides by the square root of 2. On the left side, the radicals cancel, leaving x. But on the right side, that's no longer the case. Unlike the last problem where we had a radical 3 over a radical 2, and radical 2 over radical 2, as we saw in this last one, there they canceled because they were the same. Here they don't, because these have different values. So instead what we do is we use what's called rationalizing. To rationalize means that you multiply the numerator and denominator by a quantity equal to 1. So in this case, what I want to multiply this fraction by is this square root of 2 that's in the denominator. Rationalizing by the denominator. Now the reason for that, when you multiply a square root by itself, as we see going on here in the denominator, it becomes the whole number. If we consider the square root of 2 times the square root of 2 is the square root of 4, we know the square root of 4 is simply 2. So our denominator becomes 2. Now let's consider what's going on in the numerator. The 2 here that's a whole number isn't affected by either of these two square roots, so it will remain a 2. The square root of 3 times the square root of 2 produces a square root of 6. Now, as I mentioned on the last problem, once you do that division, you need to make sure that the answer you got is in its most simplified form. In this case, the whole number 2's are going to cancel each other out, in which case x is simply the square root of 6. And there again, the square root of 6 is already simplified, so that tells us the length of each leg would be the square root of 6. All right, let's look at another one where the hypotenuse is not a whole number and doesn't have that square root of 2 already in place. Okay, so on this one, here again, we're going to start it the same way. Let's let x be the length of the leg. So the length of the leg times the square root of 2 has to equal the square root of 6. Same process as before, divide both sides by the square root of 2. There on the left, we're left with x. Now, on the right, we're left with two possibilities. We could do what we did in the last problem and rationalize by multiplying by the square root of 2 in both the numerator and denominator, or we could see this as the square root of 6 divided by the square root of 2, understanding that when you divide square roots, you can simply divide their radicands. But we're going to go through it with the rationalization that we did before. So remember, we're going to multiply both the numerator and denominator by this radical 2 that's in the denominator. Rationalize in that case. Okay, so just as on the last one, when we do that, our denominator becomes 2. Our numerator, square root of 6 times the square root of 2, becomes the square root of 12. Okay, so last thing we have to check, is it simplified? In this case, the square root of 12 isn't simplified. We know, kind of off to the side here, we know that the square root of 12 is equal to the square root of 4 times the square root of 3, which would be 2 times the square root of 3, if we were to simplify. So our numerator here is actually x equals 2 square root 3, and that's being divided by 2. And there again, we can see that these whole number 2's are going to cancel, leaving x, the length of the leg, as square root of 3, which would make this a square root 3, and this one a square root of 3 in length as well. So that gives you some idea of how to use 45, 45, 90 triangle relationships to either find the length of a missing leg or find the length of a missing hypotenuse in a 45, 45, 90 triangle.